Well, I've been looking forward to this session for months because it's one of my pet favorite topics is fusion and something I'm very excited about. And we have a range of different expert opinions and expertise on stage here because we have one of the world's leading plasma physicists and scientists with Sibylle, and we have Ellen, who's at the front line building magnet systems for fusion reactors for Commonwealth Fusion Systems. If you don't know Commonwealth Fusion Systems, it's the best funded fusion startup on earth with over $1 billion of funding, and they're setting very ambitious targets, which is very exciting for everybody. But before we jump into the topic, I'd actually like to turn to Sibylle first and tell us what is fusion at a basic level and how does it work and why is it so exciting?
Well, fusion in one sentence is actually the energy that powers our sun and the earth. And in principle, what it does, it brings two small nuclei together and then energy is released. And it is actually the opposite of what we usually call nuclear power stations, where actually large nuclei are split. And actually, it's the same as on the sun, where hydrogen nuclei are fused to become a helium nucleus. And the sun core needs 10 million degrees for that. So that's not so problematic, but the sun is a little large, so we want a smaller power plant. And so we need then 100 million degrees, so 10 times larger temperatures than in the solar core. So this is a little exciting, but this is something we have already achieved. And so that's essentially the process. So it's actually mimicking somehow what the sun is doing.
You know, I have to stop there for a second, Sibylle, because you just said that reaching 10 million degrees isn't a problem. Now, I have a pizza oven in my backyard in Australia, and if I get up to 350 degrees, I'm happy. So it's, what do you need? What's the actual, the hardware? You've got a picture here. Can you tell us more about it?
Yeah, we have a nice picture there, and the problem is, of course, we want even 100 million degrees, and you can imagine there's no material that can withstand that, and therefore we kind of confine our hot matter into magnetic field cages, and one of the cages is seen there, so the red part is one of the magnetic field cages. It's called a stellarator. We have one this is the one we have in Greifswald, Wendelstein 7X. And Elle will talk about the tokamak, which is the magnetic field cage looks like in a donut, but essentially it's very similar. And so we can confine these 100 million degrees plasmas, we call it, into magnetic field cages.
Fantastic. I'm sure we could go into this, and if we had a room full of plasma physicists, we could go on for hours, but I want to get to getting your hands dirty on the ground, building reactors. So what's that like, Elle? What are the challenges?
Sure. So I've been with Commonwealth Fusion Systems for about 5 years now. 5 years ago, we were at the stage where we had 1 meter long superconducting cables that we were twisting by hand. And at this point, we started building SPARC, which is our first-in-kind tokamak over here. All the magnets are made using high-temperature superconductors, which is the first of its kind in the world to do that. We started in early 2023 building this, and we're now about 60% complete with the build. And that means that we're putting a lot into it right now. We're very, very busy. We're creating tens of kilometers of now superconducting cable, and there's a big laundry list of challenges, obviously. When you're building the first in kind of anything, you're going to be tackling challenges every single day. And I can give somewhat of an example of some of the challenges that we face just on the engineering side of this. So you can see the kind of D-shaped magnets there that go around the plasma in a tokamak type system, which is has a toroidal plasma on the inside. One of those magnets, and there are 18 on the device, has a self-field of about 20 Tesla. And 20 Tesla, for those of you who are not familiar with magnets, a refrigerator magnet is about 0.01 Tesla. Something like an MRI machine in a hospital that can pull in a wheelchair across the room is 1 to 2 Tesla, generally. So 20 Tesla, these are very, very strong magnets, and that's part of the reason why they can accelerate the ions to get them to fuse inside of the plasma as well. But 20 Tesla generates, in one of these magnets, about 190 meganewtons of self-field force when it turns on. And for anybody who knows the SpaceX Falcon Heavy rockets, so one of these magnets is about 4 meters tall by 2.5 meters wide, and when it turns on at 20 Tesla, generates about the liftoff thrust of 8.5 Falcon Heavy rockets, all taking off at the same time. It's a lot of load that these magnets has to carry. So all 18 of them turning on at once, and this is just one of the 3 major magnet systems in the device, generates the equivalent of the liftoff thrust of 150 Falcon Heavy rockets taking off at the same time. It's a big engineering challenge, and kind of every day what we're doing is we're taking small-scale tests just on a materials basis, and then integrating them into larger and larger system assemblies, testing them in the environments that we expect they'll be able to see with enough margin that we are more certain that when all of this comes together, it's going to, get some shakedowns, but eventually get to the point where we're generating plasma and net energy.
Yep. I'm seeing in the audience a bunch of smiling people, and I wonder how many physicists we actually have. Some physicists in the audience. I knew only one. Maybe there's just smiley people, because everyone was smiling when you were talking about the heavy rockets and things like this. But
A lot of load.
you have a space background, right? You were working for NASA at under 18.
SpaceX, but
SpaceX, okay, almost.
yeah, close.
But yeah, so I guess expertise like that around the physics is needed in this industry as well. Do you have a lack of skilled people? Is it hard to get the expertise you need for the company?
Absolutely not.
Really?
We have a very wonderful group of people. So I joined when we were about 84 people. We're now over 1,000 at Commonwealth Fusion Systems. We have people from all over the world, some of, really next to Sibylle here, some very excellent plasma physicists. We've got a large group of people who are in leadership roles at SpaceX come over to support the effort to make fusion kind of a commercial reality on Earth before we leave and go to the next planet.
I'm not planning on leaving this planet personally, but...
Me neither.
So, on this, you mentioned the challenges. It seems like you have a lot of testing ahead of you, even once you get this stuff built. You have very ambitious goals. What's the timeline? When's your first power plant meant to be online?
Yeah. So like I said, we're about 60% finished with the build of SPARC. We're aiming for net energy from that within the next 2 years.
2 years? That's incredible. Mm-hmm. Now, plasma physicist and scientific expert, how does this sound in terms of timelines that you're looking at and expecting around the production of fusion power?
That is great. It's not a power plant, and they don't sell it as a power plant. Yeah. It's a first-of-a-kind device where you have net energy means more energy out than you put into the hot matter to heat it. It's not net energy in a sense to plug efficiency. Yes. So this is different. And therefore, so it's amazing, but it's not yet a power plant. This takes longer. This needs more. It needs to be bigger. It needs to breathe its own fuel. So this takes a longer time, but it's still amazing. I like it. And actually, they are building a tokamak, which is easier at the moment because it's well developed. We also have a tokamak in Garching, but we aim at a first-of-a-kind stellarator. We're just discussing this with one of the companies in Germany to do something similar with the stellarator. And the difference is that the stellarator can run 24/7, while the tokamak has to run in pulses, and so there we have kind of
downtime. In between.
Two different kind of approaches, but our institute is actually doing research on both.
Yeah, and with this, so I see the scale, I see the people. In a lab, how big is it in your lab? How are we talking? It would sit on this stage. It would sit in the room. How big is the space required?
Well, this is the same space about. I mean, we have you have higher magnetic fields. Essentially, it's about the same size.
Yep.
The Wendelstein X is a little larger because it's like a bicycle tire, while the tokamak is a little more compact. But it's our tokamak is 2 meters in major radius, about so 3.5 in radius, and the stellarator is kind of 7 meters in major radius. So it's it's big, but it's not.
Not massive. Okay, so
Yeah.
interesting,
It's no
right?
eater.
And with this, so I guess SPARC is a test bed. Then it's not what I understand. It's not actually going to be feeding into the grid. What for you, Sibylle? What's your bet realistically? In what range will we see grid-connected fusion power? We can actually power our houses on and our IT systems, for example.
Yeah, there the startups have more kind of aggressive timelines. So my best guess is having a power plant, really a real power plant switch on in 20 years' time, because there are many more problems to be solved than just such a very great experiment that shows that it can work, which is already a great success in 2 years' time. I'm very impressed. So no problem, but I still think it's 20 years to go until you have a power plant that goes to the grid.
You know, it's fascinating because many of us were here, I'm sure, this morning as Professor Rockstrom talked about the fact that we need to decarbonize today. We need to bet on technologies that we've already proven. The problem is, for me, I love fusion. I'm really excited about it, and I feel like we should invest in it, even if it's a 20-year timeline. How do you sell this to governments? How do you sell this to private funding when you say we need 20 years more before we'll get a payback?
It has improved, to say the least, because I mean we would never want to compete with renewable energies. Having said that, I mean to go to 100% CO2 neutral in an industrial country is not so easy, and we have at the moment 60%, 62 renewable electrical power in Germany, but much less in heating and traffic. So we are less than 40% CO2 neutral altogether. So I think there's a lot of room to go still to a completely renewable energy system, and we consider fusion a part of it. And it's actually the only energy source that we have not yet explored.
And it's tantalizing because it's low carbon. It would theoretically be base load power. It's all the things we're looking for long term. And
it would be base load, exactly.
Yeah. And I think that this is, it's interesting to see the transition with funding right now, and we'll get back to that again a bit later. But before we do, Ellie, now your timeline is much more aggressive, we'll put it that way. Sibylle said that startups are, have this race to the finish line. I mean, you left SpaceX, you must have believed the story, and do you still believe it, and you want to reach this timeline of, when is the grid timeline for power to the grid?
Sure. So we have SPARC, which is our scientific demonstrator, the tokamak that's turning on within the next 2 years. All of the learnings from that we are already starting to translate into ARC, which is our first commercial power plant. We have ARC sited already, so we're actually starting construction on the location that it's going to be right south of Washington, D.C. And we're expecting that to turn on within the early 2030s. So not too far off. Like Sibylle said, definitely accelerating or ambitious on that timeline.
Yeah. Well, it's interesting too. I mean, the difference between sometimes this American startup approach, it does push things forward. If you just throw down a line in the sand and say that's what we're going for, it's amazing what can happen. I guess maybe following up on that, what would you want now? What do you need to make, if you're going to make this very ambitious timeline happen, what do you need? Do you need government support? Do you need more money? It seems like you've got a fair bit of money.
Yeah, I mean, honestly, I would say right now we are heads down focused on execution. A lot of what's coming, I think, in the near-term future is we're approaching this almost the Kitty Hawk moment of fusion right now, where we're flying for the first time within the next few years. But what comes after that I think you can talk to anybody in the aerospace industry. Turning a flying machine into an airline industry is a whole set of challenges. And to be able to start thinking now about things like maintenance, about regulation, about industry trade and training, about workforce creation, like we are not just creating a new technology here, we're creating an entire industry that we're hoping to be worldwide. So really thinking about that and the level of challenge that's going to be, the level of people, the number of people we're going to need to be really pushing that forward is significant.
I think the issue of collaboration, generally when we're decarbonizing economies, we have to find new ways of working. And I feel like in sustainability, collaboration has to take on a new level to be successful. And I wonder, a research institute like Max Planck, you're collaborating with people globally. Do you work closely with your US partners as well?
Yes, in fact, we do collaborate with, for example, Commonwealth Fusion Systems. We have a collaboration contract. They even have stolen a few of our people. No problem. And we are also...
I hope they put it to good use, though.
This is all fine, because we really want to join the collaboration also when the machine is ready. It will be exciting, so no hard feelings. And in Germany, we do collaborate with the German startups as well, and actually we aim at building such a scientific demonstrator like they do for tokamak. We would like to do this for the Stellarator because we think due to the 24/7 capability, this might in the end even be the better power plant. But this is a friendly competition. So this is what we would like to do with a German startup. So we are not shy anyway in the collaboration with the startups. We like them, no problem. This is really great. I think we work best together if the startups they are a little, in particular in our German bureaucracy, so startups have it a little easier they have much less boundary conditions when it comes to building things. Or, I like them that they can really go forward with, and then we can join forces.
Yeah, that's fantastic to hear. And I guess there's a different landscape in the US. I assume, has anything changed for you with the Trump administration?
I think there's a general understanding that energy is a bipartisan pursuit, and the pursuit of energy is a bipartisan pursuit. So I could get into that up here, but I think maybe...
I have to ask, as the moderator, I have to throw that question in there.
Yeah.
And I guess here in Germany, we have a couple of MDBs coming later on for sessions this afternoon. How's the support from government? Do you need more? Do you need more from the private sector? What do you need in Germany?
Well, it has improved, by the way. So we really had a hard time after the Fukushima accident because people mixed up fusion with fission. This was a problem for us. Now the support by government is very good. They also have written it in the coalition contract. And as I said, now we have one problem. It's in Europe, I would say it's a tenth less money, a factor of 10 less money from private companies to invest in such startups. So we would need a little more federal and state money to do a similar stuff, and we would like to do it together with our startups, but they do not get billions of euros, maybe a few hundred millions is the maximum. So that's really a discrepancy between Europe and US.
Yeah, it's I think it's one of these things. Is there anyone here actually working in fusion? Is anyone in the audience actually in fusion? So general sustainability people. But I think it's even the funding market in sustainable investments in tech, it's been slow for a while. And I think, Europe, they don't give out in the way they do, for example, in California. I think that's just a given. If there's a good idea, people just go crazy in this way and they just give money. But I guess one other thing is, you talked about some of the challenges that aren't solved before. What are they? Could you extrapolate more on what the challenges are that we haven't solved yet?
Yeah, once we have the scientific demonstrators, what one can do now, the next point is, for example, how do you get the fuel? And so this needs to be bred in the power plant in the future. So this technology has not been proven yet. And we also need to test the materials who have to withstand this major challenges, neutron irradiation, heat, and all of this. And this probably you also need for regulation, and we, by the way, need the regulation in Germany as well. So there are still, on the technical point of view in particular, unsolved issues. And then on the physics side, you want to make it even better. I mean, the first airplane was also not a jet, right? So you also want to improve there as well.
Yeah, interesting. Would you have anything to add to that?
A lot of my mind right now is focused on maintenance of our future power plants. So, over time, to what degree we're going to need to maintain, replace, make sure that all of the different parts of these plants are working as they should for sustainable energy generation or electricity generation.
Yep.
That's what's big on my mind right now.
The major point is exactly there, the high availability. You don't want it just to demonstrate, you want it really long-term, that it can contribute to the grid, and you don't have to, you don't want it stopping all the time, right? So this is really a major issue we have to make sure.
Yeah.
Interesting.
I would say there's maybe 6 major milestones that a lot of fusion companies or fusion demonstrators need to hit. And the first one is a stable plasma. The second one is being able to heat that plasma, as Sibylle was saying, to over 10 million degrees Celsius, ideally up to 100 million degrees Celsius. The third one is to get that plasma confined enough and dense enough that there are enough fusion-relevant reactions that is in a regime that's useful to us. I would say the fourth, which is maybe the eureka moment, is where you have net energy out of the plasma reaction. And that's net energy, not net electricity, but net energy, so you're generating more than what it took.
Yep.
And then 5 and 6 are you're generating net electricity, so you're drawing a bigger box around the system, and you're getting electricity out to the grid. And then the 6th one is economics, right? You want that electricity that you're generating to make sure that it's cost competitive, because if you see a utility bill and you see, coal, gas, fusion, solar, wind, and fusion is 10 times more expensive than any of the other ones, realistically, no one's going to buy fusion energy.
Yep.
And I think we have a lot in the first 2 categories, maybe around the world, and only when you get, as you get going, only one has made it to 4, which was the National Ignition Facility a few years ago. But 5 and 6 is kind of what we're looking for. So I think when it comes to what challenges we still have left to solve, you're seeing what is it going to take to get us to 4, to net energy, with stellarators, with the tokamak, with maglev, with these maybe sheared Z-pinch approaches in fusion. But then what is it going to take to get us to 5, which is commercial electricity, and what is it going to take to get us to 6, which is cost-effective commercial electricity?
Yep.
And there's, we could spend years listing all the challenges.
All the challenges are there. So, this is the bits you don't get when you read that 2-page hype thing that comes up on your, your feed from Google saying that fusion's just around the corner. There is a lot of challenges that need to be solved, but there's technology.
Yeah, but for example, I mean, like we said, I mean, the 100 million degrees we have already achieved. We even have 500 million degrees once.
Wow.
So, I mean, the heating up of a plasma and confining, this is really done. And so we can go to the next steps.
Yeah. I mean, we are at 4 out of 6. That's not bad.
Okay.
That just means there's 2 more
it's
left.
feeling even more positive. Now, I want to put a hypothetical question to the audience. If you had, let's just say, 50 million, you're an investor, would you invest over $1 million in any well-established fusion startup? Put your hand up in the room. Who would put their money, their theoretical money, on the table? Up high, come on. How nice and high, I want to see you. Well, you've got like 20 million in this room alone. Yeah, come on. Yeah, let's have a round of applause for that. So look, it's interesting. People are getting warmed up. There's a bit of skepticism in the audience. But look, I guess one other thing, I want to get back to a bit more of the basic physics. Are we talking about thermonuclear power, not nuclear fission, but fusion? Are you heating up turbines to get the energy? How's the energy produced? I don't even understand the physics.
Same like in a coal power plant, nuclear power plant.
Yeah.
This part is the same. The major difference is that the intrinsic safety is given, so there's no chain reaction, so it's the intrinsic part that is different. but the heat and then 2 turbines. This
So
is
it's
the
really
same.
just turbines, the old school.
Yep.
Okay.
Yep. Harvest heat, heat steam, send the steam to turbines. It's a lot of the same infrastructure
Yeah.
even. So looking at sites that have that infrastructure already is one
Yeah.
easy way to reduce some of the setup costs.
But I guess 500 million degrees isn't needed for the superheated water. It's just to keep the plasma alive, right?
No, we need 100 million degrees in the plasma. You don't want it into the material. You cannot have more than 1,000 there. So no.
You're educating. I have a PhD in music, so this is. I'm getting a very high level education on stage. But
Yeah. One very valuable thing that the magnets do is that they make sure that none of that plasma is really touching any physical substance.
Yeah.
You can really
but,
consider it as a cage that really shields all the walls from this hot plasma. This never touches it. Exactly.
Yeah.
But, I mean, I just
away
even
from all
starting to think about those temperatures and metals and everything else. It's insane what you're trying to achieve. It's,
Oh, we did achieve it, so.
yeah, it's happening. yeah.
Consider this done. This part is done. We have now new tasks.
Yes. One fun fact that we're going to see is fusion devices have the highest known temperature gradient per unit length in the known universe. So going from a plasma at 100 million degrees Celsius to a cryogenically cooled superconducting magnet at negative 250 degrees Celsius. All of this happens within maybe 10 or 12 centimeters. So you're getting a very extreme temperature gradient. But as Sibylle said, we have done this already.
You've demonstrated
You've
that.
done it. It's happening. Okay. I want to come to your laboratory, either in one of your laboratories, either in the US or in Germany, because I'd love to see it. It'd be so much fun.
Yeah. Just come and visit us. No problem.
Yeah, just come, Dan. Pop on over.
I'll pop over sometime. But I'll definitely have to come visit you, Sibylle, at the institute, because it's just, to me, this is really the bleeding edge of physics and science. So it's amazing that we're achieving this with our scientists in the US and in Europe. I guess we're coming to the end of our session, and I'd say, what's your hope or what's your need right now in Germany, Sibylle? What would you ask for? You've said funding already. Is there anything else you need to make it to the next level?
Yes, we need regulations. So the government started to work on that, fortunately, already the previous one. So we need regulations to be allowed to build a power plant. Mm-hmm. And indeed, I would wish for the money to build a scientific demonstrator for a stellarator, which is very similar, but in a stellarator way in Germany. That would be great.
Okay, great. And Ellen?
I would say really what we're looking for is people to start to educate themselves on what fusion is, what's out there. Our CEO, Bob Mungard, wrote a letter called Building Trust in Fusion Energy. You can just find it anywhere if you search those words on Google. But it's effectively, there are a lot of fusion companies, and especially in the last 5 years, there have been a lot that have started up. And I think it's really our job as engineers, as scientists, as responsible electricity generators, to make sure that what we're doing is we're really honoring the investment that has come in with producing really trustworthy metrics and data and measurements of how close we are to net electricity on the grid and how close we are to effective commercialization of electricity. So really it's just, if you're interested, learn a little bit more about fusion, maybe go read that letter, and start to talk about it. We're creating a new industry here that's going to be more and more a part of our normal reality within the next decade. So
fantastic. I think
people who are excited about it.
Well, it's been a real pleasure for me being on stage with you both. Thanks for taking the time. Thanks for coming here. And I hope we can do a catch-up in a few years' time to see.
Yeah, you will visit us now.
I will visit you. I have to. Yeah. This is a given.
Yeah.
And apart from that, I want to have a catch-up to see your timeline. So I have to get you back in 2 years to show us the first running experiment.
I'm also very excited.
Yeah.
Let's see.
Okay, both of you then. We can just repeat this again.
Excellent.
Thanks so much, Sibylle. A pleasure. Thanks so much.
Thank you.